Hello friends, welcome to Joy of Life. So today we are going to look at another medium level problem from Leetcode. The problem number is 98. So the problem is validate binary search tree. So given the root of a binary tree, determine if it's a valid binary search tree. So a valid BST is defined as follows. The left subtree of a node contains only node with keys less than the node's key. Okay. The right subtree of a node contains only node with keys greater than the node's key. Okay. Both the left and the right subtrees must also be a binary search tree. So here they have given us a couple of examples. Let's understand why they are valid and why they are not. So over here, what you see is that we have a node 2, and to the right of 2, we have a node 3, which is greater than 2. So it's fine. On the left, we have a node which is 1, so it is less than a 2, which is fine. So this is a perfectly valid binary tree, and we should return a true here. But for the tree over here, we have a 5. So to the left of 5, we have a 1, right? Which is fine. To the right of 5, we should be having values greater than 5, not less than 5. So this is invalid. So basically for every node, so if the node is denoted by X, okay, so this should be greater than X, strictly greater than X, and this should be strictly, the left should be strictly less than X, right? So, and this is valid for all the subtrees as well. So in this case, if I say this value is Y, then it should be greater than Y, it should be less than Y. But there is a caveat to it, right? If it is less than Y, can I put a value of -3 over here? Of course not, because this tree over here, this tree is a valid tree. This is perfectly valid. But this tree over here becomes an invalid tree. Okay, so that's why we have been given with a constraint over here that both left and right subtrees must also be a binary search tree. So just keep in mind, if I have this tree over here, then this is a subtree, right, of this entire tree, and this is not valid. So we have to ensure that the subtrees are also valid. So this rule applies to the entire hierarchy of the tree. So as I always recommend, do give it a try before you look at my solution. So, but I highly recommend that you come back and check out the video as well in details, because this is a very common interview question. This is asked very often in tree problems. So I highly recommend that you come back here, watch the video, understand the code, and understand all the bits and pieces of it. And over to the board. Let's check out the solution. So what I have done is I have taken a tree over here, and we need to come up with a formula so that we can validate that this is a valid binary search tree or not. So we are going to establish some rules, and based on that rules, we are going to validate this, and then we are going to translate the same into code in our lead code problem. Okay. So let's say we don't have anything. We don't have a tree at the moment. So if it is just a null, is it a valid binary tree? Just we have the root as null. So yes, this is a valid binary tree because there is nothing, and if there is nothing, I cannot say it is invalid. So it is definitely a valid binary tree. Okay, so this is zero node binary tree, I'll say. So this is where we are establishing our base cases. Okay, so if I have now coming to the second part of the problem. So if I have a one node binary tree, then what could be my value that is acceptable for this binary tree? Basically, everything is acceptable, right? If I put a negative 1 billion, it's fine. If I put a positive 1.6 million, it's fine. There is no restriction basically. So everything is a valid input, right? So let's build the tree. Let's try to reconstruct this tree based on those inputs. Okay, so let's start with the root. So let's try to reconstruct this binary tree, and let's look at the constraint at each of the steps, right? So if I have to construct just a single node, what we have talked about, the limit, the minimum could be negative infinity, and the maximum could be positive infinity. There is no limit to it, right? So let's say in a situation like this, what I choose is a 20. So we are just following this tree. So 20 is a perfectly valid value that is falling inside this range. So let's define this range in our own way. So what I can say is that this is my min, right? And this is going to be my max. So the value should be in between this range, and what I choose is is indicated by, say, a val. So at every stage, we'll come through this min, max, and val. So what happens in a binary tree is that you can have a left child and a right child, right? So here is a left child, and here we have the right child. right? So for the left and the right child, what are the valid values? So this one should start, this one should start from 21, right? So let's say if we have this notation over here, the one that we have established over here, so we have min, max. So this is the constraint that we can say, given a min and a max, when we choose the val has to be greater than min, so it has to be greater than 20, and val should be less than max. So in this case, we know that what the value that we need should be, and how far this can go, how far we can take this value to. Actually, there is no upper bound to it, right? So it should be less than infinity, I'll say, right? Because if I have to put a value, we have just one constraint that it should be greater than 20, right? And for here, it can go down up to negative infinity. I don't mind on that, but it should be less than 20. So with these two constraints, let's say I choose a 10, which is a perfectly valid value over here, and I choose a 40. So yes, 40 is also lying in this range. So we are good. So again, from this position in the tree, what we can do is we can fork out two childs over here. For 40 also, you can fork out two childs. Now coming to this side of the tree, coming to this right of 40, what we have is we should say that I need any value which is greater than 40, and I have no constraint on my upper limit, so I will keep that to infinity. Similarly for the left, so you see that the rightmost edge and the leftmost edge does not have a constraint, because does not have a min and a max constraint. So for this guy also, we need something which is less than 10, but it can go down up to infinity. Now these two guys over here, the right of 10 and the left of 40, will have a little different calculations over here, but they are adhering to the same formula, which will come to it in a minute. So for this guy over here, what we know that we need a value certainly less than 40, right? So I know my upper bound is 40, and just observe that here we had a minimum which is 20, right? We got a minimum from this side because he was on the right. So this minimum should be there, right? So we have to pass this minimum value. So we know that it has to be greater than 20, right? Had it been less than 20, it should go to that side. So that's why we are passing this minimum over here, right? So this min is coming all the way to the left, right? So similarly for this guy, what we know is we need a value which is certainly greater than 10. So we will put a 10 over here, but we cannot exceed this 20. There was an upper cap over here, right? Because if it has been more than 20, it should go to the right hand side. So here my constraint becomes a 20, right? So let's say I choose a value of 6 for this node, which is less than 10, but greater than negative infinity, it's fine. We choose a 15 here, which is greater than 10, but less than 20. Yeah, this is fine, perfectly fine. So for 20 to 40, what I choose over here is a 35. And for 40 to infinity, I choose a 45. Let's try to reconstruct this part of the tree 35 first, and let's see how things goes wrong when we doesn't do it correctly. So this branch over here can take anything which is greater than 35, but it has to be less than its parent, right? So 40 was imposed to me over here, so it cannot go past, it has to be less than 40. And for this guy, it has to be less than 35. And what we saw over here is we have a constraint on 20, right? So it has to be greater than 20. So we put that constraint over here, right? So now for this node over here, for 35, let's say we are not putting anything, we are putting a null on the left of 35. And here we are putting a 42. So the moment we put a 42, we can see that we are violating the constraint. We are not in between min and max. We have exceeded the max. So the ideal place for 42 would have been on the right side of 40, right? It should have gone this side of 40 and then left side of 45. So could have come somewhere here, but we cannot have this node from 35. So if you look at this form, look at this pattern over here. So what happens basically is we are inheriting the value from the parent. So for root, so I'll put the rule over here. So you look at one of the pattern and you will understand for yourself that how things are working out here. So what we have is a min and a max. and we are choosing a value in between these two nodes, right? So initially it is infinite and infinite, so whatever val we choose is perfectly fine. And from this val, we are forking out two two subtrees in both the sides, right? So what will be our range in this case? So our range basically becomes, so if I have to talk about the range, so here I should be less than val, right? And I should be greater than min, right? And on the other side, it will be greater than val but less than max. So you see over here how this relation is simply depicted with the help of this node over here. So val is just coming from, this guy is coming from these two sides and acting as a barrier to it, whereas min is falling over here and max is coming over here. So you see that is true for every node. So you can see that this is valid for all the nodes. So 20 is coming over here as a min and a max, it's working for both the nodes. This infinites are falling over here. Same goes for this guy. 10 is falling over here. This is falling over here. So again for 40, we'll see the similar thing. It's falling over here. This is falling over here. This is coming here, and this is coming over here. Similarly for 35, this is falling over here. So this becomes our building block for this problem. This is how we are going to impose our rule basically. So if I have to, I have shown you graphically how it happens, how this all is falling into place. Now if you see for this tree, let's say for this tree, if we have to do in a tabular fashion, then I could simply tell that I have a min, I have a max, and I have a val. Let's say my min and max was null initially, which denotes a infinite. That means we don't have a range over here. So val I choose is a 20. So 20 is perfectly fine, right? This is the root node that we are talking about over here. So now we are going coming to the left and the right subtree. So this is, let's say this is left. So basically minimum still continues at null, but max we get the val, right? But for max we get the val, which is 20. Similarly for right, what happens? We get a min which is 20, which should be greater than min, but we don't have a constraint on the null, right? And we choose the value 10 and 40, right? So we put a 10 over here and a 40 over here. Now let's say we are doing for 10. So 10 has a left and a right. So what is the minimum for uh, what is the minimum for the 10's left? There is no minimum. It continues to get a null. But maximum we have this constraint which is 10, which is val basically. So which is 10. And for right, we have a constraint that it should be greater than 10, but it should be less than the max that we have. So what is the max we have? We have a max of 20. So let's take that 20. And what are the values that we are choosing? A 6 and a 15, right? So you see how things are falling into place piece by piece. Now let's say I am doing for this 40. So 40 has a left and a right. So for 40, what we know is val, which this val over here becomes its minimum and his maximum. So val becomes the minimum. So 40 becomes the minimum, and for this guy, 40 becomes the maximum, right? So this is my minimum for right, that it has to be greater than 40, and for left it should be less than 40, right? And what happens for the minimum values? So minimum of left, so minimum of left is coming from 40's min, right? That is 20. And for this guy over here, 40 is right, we get this value from here, right? So it is a null. So 40 is left and right, we choose two value, 35 and 45. So we are done with this nodes, right? And now if you do the same math for 35, so let's do it for 35. So we are doing for this node. So let's say this is my left and this is my right. So again, we are talking about this node over here. So this node means this becomes the min for right and max for left. And looking at this node, we have a value of 20 and 40. So it has to be greater than 20, right? On this case, on the left. And on the right, what we need is this value over here, that 40 is my max. So I should be less than 40. So for left, what we do, we don't have any value, so it's fine. If we don't have a value, that's why we said that in this recursion, we are going to return a true when we get a null. And for the right, what we are doing, for the right, we are basically putting a value which is 42 and which is violating this condition. And the moment we see a violation, we are going to return a false. But if we don't see any violation down the line, we are going to return a true. So this is the solution all about. Let's see how this looks in the code. So basically the function that we talked about deals with three of the parameters, right? So let me create a overloaded function over here. We'll use the same name, is valid BST, but we need three things over here. The val is represented by the current value which I'll get from the node, so that is fine. But what else I need is a minimum and a maximum. So minimum and maximum tells me what is my range. So as per we have done the base condition. So if we see node to be null, in that case we can simply say that okay, I have traversed down to the last node of this tree without seeing any problem. So let me say this tree is completely valid, right? Otherwise, what we are going to do, we are going to take the val out. It's not required, but I'm just doing that so that you understand it easily. And we have the same min, max, and val kind of notation. So you remember that min can be null initially, right? So we should impose this check when min or max is not null, right? So I'm just putting a constraint min is not null and then val which is less than or equal to min. In that case, what I can say is that I will be returning a false. Is that if a min value is passed to us, because initially will be passed with a null. So let's put that in place. So initially when I'll be calling this, I'll be calling with a bunch of nulls so that it never goes inside this check. So whenever this min is not null, what we are going to see that if my value is less than or equal to the min, that means my value is not in the range, right? And same check goes for max. So if max is not equals to null and then val is greater than or equals to max. So if my value is greater than or equal to the max value, then in that case I'm going to say false. So this is the same false which will stop this tree over here. So I have a max 40, I got the val as 42. So in that case, I'll be returning a false. If not, what we are going to do is we are going to check the right and the left of this tree. So I found this node to be fine. Then I should spawn two checks on the left and the right subtree. So I'll be calling is valid BST in the node dot right, and I'll be calling is valid BST in node dot left, right? So what happens is, I know this statement doesn't look good, but I want you to understand over here. So we are passing the min and the max, right? So what happens is in this statement over here, or going by this formula, what you see for left, for this left subtree, what basically happen is min remains the min, but max becomes the val, right? So for the left subtree, min remains the min. So min, there is no change, but max we are reducing. We reduce the max down to val. And for right subtree, what happens is we have to be greater than the value, right? So we pass the val as our minimum, right? And our max remains at max. So if I ever hear a false back from them, I am going to send that back. So let's quickly look at one of the valid example, a very short tree. Say 3, this is 2, this is 4. So 3 will call 2 and 2 is fine. So 2 will call its left with a null, right with a null, right? The recursion tree will look like this. So he will return a true. He will return a true. So both are true. So I am going to do an AND between this true and send that back, right? Now just think of a scenario over here, invalid tree, right? So what happens is 3 says I'm fine. Let's check my child 2. 2 says I'm fine. Let's check my left. It gets a null. Null sends him back a true. He, 2 calls it right. He sends back a false. We do a true and then false and we pass back a false. That's how we propagate in this function. So that's what we have been doing over here. Definitely, when we are calling this function, we are going to return what we get from this function. So this is the code all about. There is nothing much to it. This is exactly it. This is the exact algorithm that we have talked in this board also over here. So let's run the code and see how it goes. Keeping my fingers crossed. Yes. Let's check for a wider range of test cases. And yeah, we are good. We have a 0 millisecond solution, which beats 100% of the solution, which is pretty decent, right? So I hope you got the entire thought process behind this, and at every step we are breaking the things up and passing it to both our branches, and then coming up with the solution that the tree is a valid BST or not. So do let me know what you think about the solution. If you think the solution is helpful to you, do give it a like. The channel is growing in a quite a good pace. We have reached 160, another 10 subscriber in just a single day. So it feels nice, and this is our 50th problem for Leetcode. I hope I was able to give you some idea on some of the problems. I may not be perfect in all the videos when I started. I know some videos were not that intuitive, some are slow, some are not good. But I'm sure if you have watched till this point of the video, that means you have surely liked the video. So if you think this video is helpful, do give me a like, do share and subscribe as well. Do share with your friends. Let the channel grow. And let me know if you want me to solve any particular problem from any platform or from any offline problem that you have in mind. I can help you do that. If you want to learn any particular topic also, you can just drop me a comment in any of the videos, and I'll definitely try to come up with a video wherein I uh, explain you every bits and piece of it as far as I know. So yeah, that is all from this video. See you soon, guys. Have a great day. Be safe and take care of yourself.